Well, good morning, everyone, and welcome to the first session this morning. I'm Jim Brown. I was going to chair this afternoon, but since Doreen isn't here, we'll just do a switch. So our first speaker is none other than David Wallace from Southern California, who's going to talk about thermodynamics as a control field.
Thank you. I wasn't able to make the session yesterday. I suspect the first few minutes of the talk are going to overlap a bit with some of what's been said, and in particular some of what Wayne said. So apologies for that. On the other hand, I think various other people also weren't able to make yesterday, so for your benefit, I will do a previously on thermodynamics as a resource theory. So if you look at, from a philosophy of science point of view, if you look at thermodynamics, the obvious temptation is to say, well, this is one of a large family of sort of X dynamics theories like chromodynamics or magnetohydrodynamics or electrodynamics or geometrodynamics or whatever. And these are all theories which you can sort of characterize as saying what they're about is there's a space of states, and the theory has a dynamics, which is what the system will do, never mind what you're doing in the setup, and the dynamics will say the system's here at some point, it'll evolve to this point, and then it'll evolve to this point, and it'll evolve to this point. And simplifying a lot of the history of physics, what you're doing in studying a dynamical theory of that kind is trying to understand what those dynamics are, try to understand how states transform to other states, and in practical physics, actually trying to calculate properties of that dynamics. And if that's your picture of dynamics and you're interested in the question of how one theory might reduce to another theory, you've got a fairly natural way of thinking about it that says, well, here's my high-level theory with its states and its dynamics, and then here's my low-level theory with its states and its dynamics. And the way we understand reduction is something like we work out how, what the relation is between states at the low level and states at the high level, and ideally we do it in such a way that the dynamical maps at the high level and low level commute. So in other words, in that kind of picture, the high level dynamics is a sort of coarse-graining description of the low level dynamics. I have some many-to-one map from the state space of the low level theory to the state space of the high level theory. And we try to kind of derive what the dynamics of the high-level theory is from that map and from the dynamics of the low-level theory. And hopefully if we did that right, we managed to get back the dynamics we antecedently thought was correct for the high-level theory. And a lot of that game is that we have a kind of independent characterization of the high-level theory, at least in idealization, and we're trying to recover that characterization from the low-level theory. I'm not going to go into too much of the details of how that goes, because thermodynamics isn't like that at all. Thermodynamics isn't like that etymologically, I think Wayne touched on this yesterday, but more importantly, thermodynamics isn't like that dynamically. If you ask what's the dynamics of thermodynamics, what do systems do when they're just evolving by themselves, the answer is basically really boring. They go to equilibrium and they stay there. If there's anything that counts as dynamics in thermodynamics, and I think even that's sort of tenuous how you want to describe it, it's the principle that systems equilibrate. What does equilibrium mean? It means a system doesn't change unless it's acted on externally. That's a fairly dull dynamics. That's not a curvy line of interesting properties, that's a point. What we're doing instead in thermodynamics is that we're interested in how the state of the system transforms if we push or prod or poke it, or if we stir it, or if we take two systems at equilibrium and we couple them in various ways. In other words, we're interested in what kind of control we can have over the state of a thermodynamic system by the various sorts of external interventions we make. So in this context, people have been using resource theory as a description for that kind of setup. I've been using the term control theory. This is largely a semantic distinction. The important point is that you've got a picture of the theory as saying, okay, here is the space of states, and now here are the kind of transformations I can induce on the space of states, given the resources available to me. And now the questions are not how does the system evolve spontaneously, but which transformations are and are not possible for the system. And that also rather changes the story you want to tell about reduction relations between theories. In fact, it makes you think that any attempt to say that we're reducing thermodynamics to statistical mechanics is kind of mischaracterizing the question. So if I'm thinking about a control theory, then I start with a theory that I've antecedently characterized, maybe it's got its own dynamics, And then I want to know, well, how can I modify the state of this antecedently characterized system if I drop the assumption that it's just sitting by itself doing its own thing, and if I actually try to intervene in various ways and move the system around the space of possible states. So that's the sort of starting spiel. And the way the conference blurb describes it is that there's a sort of turn towards thinking of thermodynamics as a resource theory or a control theory. I think actually the theory was always something that, if you thought about it right, had to be understood as some kind of control theory. And that means, from a modern perspective, while historically it's very important that thermodynamics was developed as an autonomous theory, from a modern perspective it's just as important to say, okay, given a complete characterization of the microdynamics of the system I'm studying in its own language, now I want to see what the control theory of that system is. And so the main part of what I want to do in the talk, and this is going to shade into pedagogy in some ways, is just cash out how I think that kind of account of thermodynamics works, starting with a classical mechanical description of the system. It could be quantum, there's no deep difference for my purposes, but starting with a mechanical description of the system, and then just asking, how can we characterize the kind of sets of control operations we can make on the system, and what kind of constraints are imposed on the movement around the space of states by the control operations we have available. And that means I've got a sort of secondary title for the talk, which is Thermodynamics with and without reversibility, because one of the things I want to ask in that framework is, once you're thinking about thermodynamics in terms of the control operations I can and can't do, what kind of insight does that give us into the sort of vexed question of where the direction of time is in thermodynamics, where it is that thermodynamics ends up being an irreversible theory? And we'll see to what extent that is and to what extent that isn't linked to the related but very much distinct question of how irreversibility comes about in statistical mechanics. Okay, so here's my abstract characterization of control theory, just to have it down. I've got a space of states, and what that means could be almost anything, and I've got a set of control operations, and at the abstract level, all I mean by a control operation is it maps states to states. And the set of control operations is the set that I'm permitted to carry out. And modulo a slight technical caveat I'll get to in a minute, we naturally want to assume that the set of control operations is closed under multiplication. So if I can do x to the system, and if I can do y to the system, I can do x and followed by y. And we're normally assuming, just for simplicity, that one of the things I can do to the system is leave it alone. We get some flesh on the bones of that if we look at how that plays out in an actual control theory for classical mechanics. So I've got the word statistical here, but actually the statistical aspects of classical mechanics are going to be somewhat in the background, except, well, you'll see the way in which this is and isn't statistical. So the starting point is I've got a collection of phase spaces, call them PI, each one's got its own Hamiltonian HI, and in the first instance I'm treating these as mutually dynamically isolated systems. So my full phase space is something like the product of all of these phase spaces. There's a special case you could consider the control theory where I've just got one phase space in one system. And I'm characterizing the states as probability distributions on that, the product of that collection of phase spaces. I'll come back in just a moment to say to what extent that way of characterizing states is and isn't innocuous. So notice because I've got a Hamiltonian on each phase space, there's already some dynamics in the theory, but the dynamics is what the system does if left to itself. I'm then assuming on top of that, I've got a bunch of control operations, and I'm going to assume right at the beginning of the story that my control operations are canonical maps from the state space to itself, so canonical in the usual Hamiltonian dynamics way, in particular in the preserves phase space volume way. And if I've got a map from phase space to itself, and if I've got a probability distribution on phase space, I can pull the distribution forward using the map, and so my control operations, although I've in the first instance characterized them as maps of phase space to itself, really give me what I care about for these purposes, which is a map from states to states. And often in control theory, and particularly if we're looking at it from a resource perspective, we're interested in a particular question of what I can get out from my control transformations. And the metric we're going to use for thermodynamics here is we're interested in how much energy we can get out from the process. So if we assume that our control process is ultimately embedded in some physical system, the dynamics of that larger system conserves energy. You might imagine, for instance, that we apply the control process by turning on an interaction Hamiltonian and turning it back off again. Then, just by the conservation of energy, we're going to find that the energy we get out of applying a transformation is going to be equal to the change in the energy of the state in the process of the transformation. So the work involved in going from initial state rho I to final state rho f is minus, just by convention, the difference between the expected value of the Hamiltonian on rho f and the expected value of rho I. There are ways of characterizing what we want to get out from a resource theory that don't look at the expected energy, that look at other functions. I'm just looking at the expected energy for these purposes. And all of this, formally speaking, generalizes pretty straightforwardly to quantum mechanics. There are conceptual issues that are in play, but I want to put those aside for the moment. Okay, let me pause to address a concern that comes up a lot in the foundations of statistical mechanics literature. People get very uncomfortable in foundations of statistical mechanics, at least in some traditions of foundations of statistical mechanics, characterizing systems by probability distributions. Yeah.
You're defining the work extracted in this way.
Yeah.
But don't you need to account for possible changes in the entropy? I mean, who's to say the difference in the energy is extractable as work?
Oh, for my purposes here, that's purely definitional. So I'm just coming in and applying some unitary or some Hamiltonian transformation in this case. So by conservation of energy, that energy is turned up outside the system. I agree, it's possible that you might find that the way you've done it is such that only some of it's accessible. But for the moment, I'm just looking at how much energy is required to perform the unitary transformation, or how much energy do I get out performing the unitary transformation. I agree. There's a question about whether that's too high or too low a level of abstraction.
But maybe the key point is it's a unitary, and therefore the entropy is not changing, so I don't need to worry about the entropy.
That's probably right. I mean, hold that thought and see where it goes to. But yeah, these are unitaries. If you wanted to apply something like a completely positive map or something, then just imagine you're bringing in an auxiliary system as part of the description. Okay, so addressing this foundational question that comes up about treating states in these systems as probability maps. So, I mean, here's a classic statement of concern here. This is David Albert's statement in sort of classic nuanced, cautious position. Can anyone seriously think that our merely being ignorant of the exact microconditions of thermodynamics plays some part in bringing it about and making it the case that, say, milk dissolves in coffee? And there are similar statements of that kind in various places in the literature. For our purposes, here's why I don't think we want to worry about that. First reason, Albert's concern here, the general concern that comes up, is that our probability, that some kind of epistemic conception of probability is not compatible with giving objective explanations of goings on. But I'm not particularly committed here to whether we need to interpret probabilities epistemically. So if you don't like that and you want a less epistemic way of conceptualizing the probabilities, knock yourself out. I think I'll come back to detail this in a minute, but my talk's largely neutral as to the interpretational status of the probabilities in play. Second point, and here I am already breaking my claim I was going to stay inside classical mechanics, at least when we're considering quantum mechanical states, the analogue of the classical phase-based distribution is the quantum state pure or mixed. We don't really have the classical microstate in the right way that could be used as the alternative description of the state. So if we think that ultimately the world is quantum, for which there is pretty good evidence, then we're going to want to be able to interpret our control theory as a quantum control theory, and under that interpretation, I don't think we've got a lot of choice but to use quantum states which are in one way or another, depending how you interpret them, probabilistic, either way. And thirdly, though, most straightforwardly, Albert's criticism has bite in its own terms if we're asking about something spontaneous in a system's dynamics. It's just objectively true that milk dissolves in coffee, And so, sure, if your explanation as to why milk dissolves in coffee turns on your partial knowledge of the coffee's microstate, then you've at least prima facie got some questions to ask. But if we're interested in thermodynamics as a control theory, then the analogous argument really doesn't go through. I mean, try it. Can anyone seriously think that our merely being ignorant of the exact microstates of thermodynamics plays some part in affecting what kind of transformations of the system we can ourselves carry out? That doesn't really seem to have bite. If we're analysing a theory about what kind of operations are available to me, then there isn't anything like the same kind of problem with the idea that the operations that I can perform are affected by the information I have of the system. Okay, so much for that kind of foundational worry. What I'm now going to do is characterise sort of several different ways of filling out the details of that kind of control theory skeleton. So the skeleton is states of probability distributions on phase space, equipped for Hamiltonians. Transformations are symplectomorphisms on the space. But they're not necessarily every symplectomorphism, and I want to sort of look at what sort of restrictions we place on the available transformations, and what we can make, and how we're to understand those in the context of, in particular, issues of irreversibility. So I firstly want to consider what you might call reversible thermodynamics, where there just aren't any constraints of that kind. So you can carry out absolutely any symplectomorphism you like. You have enormously fine-grained control of the physical system. So what can we say in that situation? Well, canonical maps preserve the Gibbs entropy. That's an easy mathematical result. You don't need to think that the Gibbs entropy has got anything to do with capital E entropy to know that that's just straightforwardly mathematically true. And what I'll call reversible thermodynamics permits every map that satisfies this. And in doing so, it actually creates a sort of artificial expansion even beyond what we can physically perform, because not every volume-preserving map is a symplectomorphism. But for the moment, I just want to consider, okay, suppose I can just perform any transformation I like on the system, provided only it keeps to this minimal requirement that applies to canonical transformations, with that it preserves the Gibbs entropy. So often one talks about thermodynamics in the context that one only has various kind of coarse-grained control of the system in various ways. To start with, I want to drop that entirely. We have absolutely complete, maximally fine-grained control of the system. What we do with it? Well, here's a nice way of characterising what we can do about it. Suppose we want to get work out of the system. So the system's described by some distribution. The distribution has a certain Gibbs entropy, which roughly speaking you can think of a measure of the volume of the distribution, the extent it has over phase space. How's the best way you can get energy out of it? And I hope it's intuitively reasonably clear that the best thing you can do is to transform the system down to as low an energy state as you can possibly manage. If you didn't have to worry about reversibility, if you didn't have to worry about preserving the Gibbs entropy, then of course it's obvious what you do. You do a control operation that maps every state down to the ground state of the system, and you get out the entire difference between the expected energy of the system and the lowest energy of the system. You can't do that, of course, because that wouldn't be reversible as a transformation. That would be squashing the probability distribution down. So what we really want to do is we want to pack the probability distribution as low down in the space of energy states as we can manage while preserving its Gibbs entropy, loosely speaking, while preserving its size. So suppose we've got our distribution, it's got Gibbs entropy S, it's got expected energy E. That best control operation available to us is the one that's going to map rho to the state that minimises energy for that particular Gibbs entropy. And we know how to work out which that state is. When I'm saying energy here, I'm often just dropping the word expected, but always think about it as there in background. So as an easy mathematical calculation, the extremal state here is the canonical state. It has that familiar Boltzmannian form, where T here, for the moment, is just uninterpreted except as the factor in that calculation. So your best option, if you have complete reversible control of the system, is to transform the system down into the canonical state available, and then extract all and pocket the energy you get out as a consequence. So I should say here, in case it's not clear, that T is implicitly given by S here. So you work out that the canonical distribution is the energy minimizing state. You then work out what the entropy is as a function of T, and then by inverting that, you get T as a function of S. So I define the canonical energy of the system just as a function of the of the entropy, and the canonical energy of the system is the actual value of the expected energy if the system is in the canonical state at its actual Gibbs entropy. And borrowing a term from standard thermodynamics in a slightly different context than it's normally used, the free energy of the system is the difference between the actual energy of the system and that minimal canonical energy. And that free energy is the maximum work you can get out of the system. Now notice, of course, a lot of these things are familiar from various bits of equilibrium statistical mechanics, but no assumption of spontaneous equilibration is in play here. There's no presumption that the actual dynamics of the system in any way spontaneously drives it to this equilibrium state or to something that's appropriately related to this equilibrium state. All we're doing is saying that this is the minimum energy state available for that entropy. I should be clear, incidentally, I'm not giving explicit references here, given the long and tangled history of statistical mechanics. Don't assume that any technical result I give here is original. This is particular. These are well-known results. Anyway. So first thing to notice, our hands are tied to some degree by the extent of the probability spread of the state, even if we have perfect microscopic control of the dynamics. It's not true that maximal microscopic control of the dynamics lets us get all of the energy out. It's also going to be helpful, incidentally, to define what you can call the effective temperature. I say effective because, again, I don't want to say there's any connection between antecedently understood equilibrium notions of temperature, just as the rate of change of the canonical energy with the Gibbs entropy. And that T is the same T as you find turning up in the expression for the canonical distribution, and if you remember your theory of Lagrange multipliers, you'll remember why that is. Okay, so to get sort of further handle on what's going on there, suppose you've now got two systems, and for simplicity, let's suppose that their initial states are uncorrelated. So the first system has Gibbs entropy S1, energy E1. Second system has Gibbs entropy S2, energy E2. If you ask what's the most energy I can get out of those combined systems, well, of course, I can perfectly well treat those combined systems as a single system and just say that, well, the most I can do is extract all of the free energy of that combined system, which again is going to be the difference between the energy of the combined system and the canonical energy of the combined system given its entropy. But I could decompose that conveniently. The free energy of the combined system is the free energy of the first system plus the free energy of the second system plus whatever else is left over. So call the thing that's left over the free energy of thermal mixing of the two systems. And that free energy of thermal mixing depends only on the entropies of the systems. So to visualize that, you've got your two systems. Your strategy for getting the maximum work out is, first of all, reversibly transform the first system down to its canonical state and pocket the energy difference. Then transform the second system down to its canonical state and pocket the energy difference. And then transform the combined system from the product of these two canonical states at different values of the effective temperature down to the that canonical state of the combined system which minimizes entropy, which in fact turns out to be the one in which they're at the same effective temperature. And again, some of these should look quite familiar as formulae from the thermodynamics we're used to. Let's push that further. Suppose I do have two systems, system 1, system 2, and in both cases the effective temperature of the systems is T1 and T2, and suppose I want to carry out some infinitesimally small control process that takes energy delta E1 out of system 1, then you can prove, even under the full assumption that you've got arbitrary reversible transformations available, the best you can do for work is given by that formula there, which is the familiar Carnot formula for efficiency there. So the closer the two systems are in temperature, then the closer that factor there is to 1, and the less work you can get out from the process. Pause on that inequality. Call that the Carnot inequality. You can't do better than that. But to be fair, in reversible thermodynamics, there's kind of a sense in which you can't do worse than that either. Because suppose you carry out a transformation of this kind where the work you get out is less than the amount you're allowed to get out by this maximum. That has to be, just as a matter of conservation of energy, that has to be because you've increased the free energy of one or other or both of the systems in isolation. You've driven one or other of those systems away from its individual canonical state. And so if you're doing reversible thermodynamics, you can always get that energy right back out again by doing another reversible transformation. But it does mean, for instance, that if you give me the sort of classic heat bath situation, I've got some system T2, some system here and some system here, and I've already extracted all the energy I can out of this system and this system separately. Even given arbitrarily fine control of the dynamics, the most I can do to get usable energy out of the systems together is to get it out at the Carnot limit. So we have a substantive constraint here about what we can do energetically, even given perfect control. Okay, so much for reversible thermodynamics. I now want to see what happens if we restrict the control operations available a bit. And the way I want to restrict it is as follows. I want to imagine I've got some coarse-graining map. I'll tell you what I mean formally with that in a moment, but informally I mean some map that preserves only some of the coarse-grained structures of states. And the coarse-grained map is supposed to be some description of the limitations of my ability to intervene on the system. So I can intervene on the system so as to adjust the coarse-grained details, but I can't intervene on the system in any controlled or predictable way to manipulate the fine-grained details that are invisible to the coarse-graining map. That's the kind of intuitive setup. I'll tell you how it works formally in a moment. So what I require of a coarse-graining map in the abstract is, well, firstly, it is a map from states to states. Secondly, it's a projection. If I coarse-grain twice, it's the same as coarse-graining once. And I'll require that the coarse-graining leaves the expected value of the energy invariant. I'm actually going to allow it to leave it really, really close to invariant, but for the moment, leave it invariant. Arguably optionally, but for the purposes of the control theory that I want to think about, I'm also assuming that it leaves the entropy non-decreasing. So the Gibbs entropy of the coarse-grained description is at least as big as the Gibbs entropy of the fine-grained description, and you get equality only if the original fine-grained distribution was already coarse-grained in the sense that it was invariant under the action of C. Okay, quick caveat, because this is really frequently a source of confusion when I talk on this stuff. There is no suggestion here that the coarse-graining map is actually physically being applied. What is physically being applied in this process is the system's own reversible dynamics, the entirely unitary or Hamiltonian transformations that I perform on the system. The coarse-graining map is purely mathematical. It's not that any suggestion the system actually gets coarse-grained. Okay, in that case, why does it matter? Let me say what I mean by a coarse-grained control theory. I want to say, I've got my set of control operations, and that set of control operations, jargon term, forward commutes with the coarse-graining if this equation holds for any reasonable length sequence of control operations. So, in other words, suppose I do the following two things. Firstly, I try saying, I'll apply the coarse-graining map, then I'll apply a whole sequence of control operations, and then I'll coarse-grain again at the end. Or suppose instead of that, I say I'll apply the coarse-graining map, apply the first control operation, coarse-grain again, apply the second control operation, coarse-grain again, apply the third control operation, coarse-grain again. If I do either of those things, I get the same transformation of the state space. Ideally, you'd like this to hold for arbitrary n. For technical reasons tied up on the Poincare recurrence theorem, asking for it to apply for arbitrary n isn't realistic. So n is stupidly large but finite. 10 to the power of my phone number, say. And then, more jargon, if I've got a coarse-graining C, and if I've got a bunch of control operations that I've mixed up forward compatible and forward commute, it doesn't matter, that's forward commutes of C, then a particular state is forward compatible with both of them if I could have put that state at the front of this chain without affecting the result. So in other words, if I've got some state such that I start with the state, I apply all the control operations on a coarse grain, I get to the same place as if I start with a state, coarse grain, apply the first control operation, coarse grain, apply the second control operation, coarse grain, and so on. So all of the states which are themselves coarse-grained are forward compatible in that sense, but a bunch of other ones might be as well. And what's the point of all of that formalism? Well, the idea is supposed to be something like this, that the transformations are insensitive to the fine-grained details in the sense that it doesn't matter from the point of view of working what happens with them if you apply the coarse-graining map at a few intermediate points during the story. So you could imagine a situation where that wasn't the case. You might imagine that, say, control operation 2 was extremely sensitive to fine-grained things control operation 1 had done, such that applying the two operations in sequence didn't get you the same result as if you'd just replaced the result of the first operation with a coarse-grained state. I'll give you a concrete example of this. People are familiar with the spin echo experiment? So I set up, I set up my system, I apply a transformation to it that looks like it kind of randomizes its spins, but I then apply a magnetic pulse that flips all the spins, and I apply the flip of the transformation, I get right back to where I started. So a control operation whose coarse graining map is something like, pretend the system's totally randomized, coarse grain map is totally randomized the system, and whose control operations included the spin echo transformations, wouldn't count as a theory whose control operations were forward compatible with that coarse graining. Because if I apply the spin transformation, randomize, and apply the reverse of the spin transformation, I don't get back to the same place as if I applied the spin transformation, reversed the spin transformation, then randomized. Okay, so that's a fairly abstract general framework for thinking about restrictions on control operations that I have available. And it's inspired to some extent by the fact that we have something very similar going on in the dynamical story of non-equilibrium statistical mechanics, although that's a story for another time. To get some sense of what's going on there and what sort of restrictions that means. So now suppose I've got a state, rho again, and it's got energy E, and let's suppose that my control theory is not the full reversible one, but it's a control theory that's forward compatible with this coarse-graining C. So you can define the coarse-grained entropy by saying, okay, the coarse-grained entropy of a distribution rho is the ordinary Gibbs entropy of what you get if you coarse-grain rho. So again, notice there's no implication here that we're physically applying the coarse-graining map. This is a perfectly well-defined function of the original distributions. It's just the way you calculate the function is you apply the coarse-grained map and then you work out the Gibbs entropy. Why does that matter? Well, the coarse-grained entropy, given the way we've set all this up, is none-decreasing under control operations. So the fine-grained entropy, remember, is invariant under control operations. But given the way we've structured it, then the coarse-grained entropy is never going to go down under control operations, and except in special cases, it's actually going to go up under control operations. Yeah?
Question, clarification.
Yeah.
You defined a bunch of properties of the coarse-graining map, but you didn't pick out a use of coarse-graining map.
I haven't, absolutely not, no. So if I've got a framework here.
Like that equation is, for any map that satisfies those properties, you could completely...
Yeah, C is a free variable here. So for each coarse graining, there's a coarse-grained entropy appropriate to that coarse graining. And so the coarse-grained entropy that's relevant for a given control theory is going to depend, okay, what's the coarse graining that this control theory is actually forward compatible with, if any. And if you then say, well, the coarse-grained free energy is just the ordinary free energy you get given the energy and the coarse-grained entropy, then I tend to think trying to do mathematical proofs in the middle of talks doesn't work, but so I'll just state this for the moment, but we can talk about the details. Hopefully it's reasonably clear that if my control theory is forward compatible with C, then the upper bound on the energy I can get out isn't the full free energy, it's the coarse-grained free energy. So if my distribution, for instance, has a very fine-grained microstructure that the coarse graining washes out, and if my control theory is forward compatible to that coarse graining, which is to say it doesn't give me control of those very fine details, then even though somebody who had full microscopic control could map that very fine-grained distribution down into a very small area of phase space and get out a lot of work, the most I can do with a control theory that commutes with that coarse graining is sort of map the coarse-grained distribution down to that same space and get out a lot less work. Okay, so to actually, that was a bit abstract. To illustrate that, let me mention a couple of coarse grainings that do important foundational work here. And the most obvious is equilibration coarse graining. So I've got a bunch of systems. The equilibration coarse graining just maps every system state into the equilibrium, the canonical distribution at the same energy for that state. So the way to think about that intuitively now is if we're thinking that the system proceeds under its own dynamics effectively to equilibrium, in other words, it proceeds to a state that isn't the true equilibrium distribution, but is indistinguishable from the equilibrium distribution from the point of any intervention I can do, then from the point of view of a control theory, which doesn't allow me to interfere with systems' approach to equilibrium, the best I can do is what I would be able to do if the system was actually in that equilibrium state. And in equilibration coarse graining, then the individual elementary systems have no free energy at all. Just by construction, they have no free energy at all. The only available work in a system of this kind is the free energy that I can get out through thermal mixing. There's a way I could have generalized the story to include sort of externally controllable parameters, and then you can get out work from that as well, or other conserved quantities that you can get work out from chemical mixing or something. But at this level of analysis, the only available free energy is free energy that holds from allowing two systems to interact in a controlled way. An individual system, I can't get any free energy out from at all. It's different coarse graining. Suppose I have something like the notion of macrostates we're used to in Boltzmannian statistical mechanics. So I coarse grain, I decompose my phase space into a bunch of subsets which between them, which are disjoint and which combine to be the entire phase space. So that got something like here's my phase space, and I'm decomposing into cells of probably quite different sizes. So the Boltzmannian coarse graining says, given some distribution, maybe it looks like that, coarse grain it by smearing it uniformly over each of the macrostates. So I replace this distribution with something that looks a bit like yeah.
Relative weight that's assigned that uniform distribution to those.
Yeah, so that's being a bit more formal about it. Work out the probability of the system being in any given macrostate from the distribution, and then replace the bit of the distribution in that space with the uniform state weighted by that amount. I can put the formula up if it's useful in discussion. So the Boltzmann style coarse graining describes a situation where I've got control of which macrostate the system's in. So I can perform a transformation that maps one macrostate to another macrostate, or I can perform a transformation that maps a macrostate to some probabilistic mixture of macrostates, but I haven't got the sort of sufficiently fine-grained control that lets me go into the macrostate and map the system to one place or another, depending on exactly what its microstructure within the macrostate is. So this is a finer grain notion of coarse graining than the equilibration coarse graining. It involves having more control than I have under the equilibration coarse graining, but less control than I have under a fully reversible coarse graining. And so here, for that reason, you've got a bit more free energy to get out. If you actually know the system's macrostate, there's some free energy you can get out by transforming it into the equilibrium macrostate at the lowest energy you can manage. So if the system has quite a high energy, but I know, but it's in quite an unusual macrostate for that energy, I can reversibly now transform it down to the equilibrium state at a much lower energy and pocket the difference as work. Yeah.
Just a quick question. Is it clear that the equilibration coarse graining is always a valid stochastic map? Or could it have some fine properties? Like it increases the distinguishability or something?
Pass is the short answer. I think it's fairly clearly defined, but I could easily believe there's a subtlety I'm missing. And in particular, I don't know. I mean, so one of the things I'm assuming about the equilibration coarse graining is it decorrelates the system as part of the transformation. So if I had if I had some state that was correlated or quantum mechanically was entangled, then first of all I just map it to a product of marginals, and then I map each marginal to the equilibrium state at that point. But I'm not sure, so I'd be interested to know if it did. Okay, so let me draw some sort of molds from that. One of the questions that comes up a lot in these kind of conversations is the extent to which it should or shouldn't be the case that simply having information about a system is a resource that can be used in thermodynamics. And some of the sort of objections sometimes get made to Gibbsian ways of thinking about statistical mechanics is something like, well, to paraphrase something like Shelley Goldstein, the thermodynamic entropy of a system is some objective feature of that system. It doesn't change just because I have fine-grained knowledge of that system. So I think we can sort of see in this kind of framework, as I noticed earlier, if I've got a coarse-grained control theory that's forward compatible with some coarse graining, what matters for getting work out is the coarse-grained entropy and the energy. So the smaller the coarse-grained entropy is, the more work I can get out, the higher the effective free energy is. So information about the state is a resource, but only insofar as we can manipulate the relevant degrees of freedom. So is it helpful to know the macrostate of the system, rather than just knowing its energy? Well, yes, provided your control operations are fine-grained enough to do macrostate manipulations. If your coarse graining, sorry, if your control theory is forward compatible with full equilibration, knowing the macrostate won't do you any good. Is it useful to know really fine-grained details of the microstate? Well, only if you have control operations that are sensitive to those really fine-grained details. I mean, example, is it useful to know that the system, the system of spins you've got is not actually thermalized, but is the result of applying a certain magnetic pulse? Well, yes, only if your control operations include the ability to time reverse that magnetic pulse. So, in reversible thermodynamics, any information about the state is possible, is useful rather. In equilibration coarse graining, detailed information about the subsystems is completely useless. The only thing that's useful in an equilibration coarse graining is information about the different entropies and energies of the different systems, because you can use that to extract free energy of thermal mixing. Boltzmannian coarse graining, information about the system's macrostate is useful, but the sub-macrostate information is useless. Okay, let me just use that as a sort of tool to talk a bit about one of the sort of vexed puzzles that comes up in a lot of discussion, this question of Maxwell's demon. There's been a sort of tradition in recent philosophy of statistical mechanics to say that the barrier in constructing a Maxwell demon is kind of a barrier of practice. That if I have, there's no problem with constructing a Maxwell demon if only you have really fine-grained control of what's going on and your access to a very big space of possible macrostates in which to record the information that the demon writes down. And I think one thing that you can sort of see the control theory starting point is there's sort of two different notions of Maxwell's demon in play. So the notion that comes up a lot in this kind of literature is a demon that can reduce some kind of coarse-grained entropy. So suppose so call a demon of the first kind a demon that can reduce some coarse-grained measure of entropy. So if I want to say that the Boltzmann entropy is just of a system is just the log of the volume of a macrostate, or the weighted log of the volume of a macrostate if it's spread across, then a demon of the first kind can lower the Boltzmann entropy by distributing the system very widely. More generally, if I've got in mind some entropy that's defined by some coarse graining of the kind I wrote down, then a demon can decrease that entropy just by having control powers that go beyond that level of coarse graining. What are demons of the first kind useful for? The main use for a demon of the first kind, I think, is annoying physicists. So there's a certain move, not by people who are in physics who are sort of sensitive to the subtleties of statistical mechanics, but in some other corners who'll say, entropy, where maybe they mean the Boltzmann entropy, or maybe they mean some coarse-grained Gibbs entropy, or maybe they mean thermodynamic entropy in the in something like the Gibbsian sense. That can never go down. So if you've got a demon of the first kind that's sensitive to fine-grained details that can lower certain entropy, you can use it to annoy those physicists at cocktail parties. A demon of the second kind is a demon that can violate the Carnot inequality, which is to say, a demon of the second kind can say, here's my heat bath at temperature T2, here's my heat bath at temperature T1, I can get out energy from between those systems, I can get out work at a rate that's higher than the 1 minus T2 over T1 Carnot formula. The main use of a demon of the second kind is to do things like charge your phone from the ambient energy in the room, run the national grid off the temperature around, and, to cut it long story short, to become incredibly rich. It kind of matters whether you've got a demon of the first kind or a demon of the second kind. Demons of the second kind are unfortunately impossible, because all we needed to derive the Carnot inequality was basic reversible thermodynamics. It was the assumption that our transformations preserve Liouville volume. No assumption, excuse me, no assumptions about coarse graining or your ability to manipulate a system of fine grain, or your inability to manipulate it, went into deriving the Carnot inequality. It was derived simply from the sort of maximal control theory compatible with the way the laws of physics are structured. So unfortunately you can't build demons of the second kind. And the fact that you can build demons of the first kind is kind of curiosity, but not the kind of totally rewrite the way thermodynamics works that the demon of the second kind would be. Of course, if you have a reversible thermodynamics and you happen to start off with really good knowledge of the apparent heat path here, you actually know information about its microstate that's much more fine-grained than the full equilibrium distribution. Of course, that gives you some free energy that you can get out that you wouldn't be able to get out if you had a coarser-grained control theory, but ultimately you get that out on a one-off basis, and it's still the case that you can't get out the residual energy beyond the free energy that you get out from the Carnot route. Okay, so let me just. And I suppose I should say before I wrap up. And then there's a temptation to say what the demon should do is therefore collect that information. And of course, that collected information does give the demon more resources available, but familiar stories in the literature that go by the name of Landauer's principle, etc., which for time reasons I won't recount here, tell us that if the demon decides to collect information, then the resource, the free energy cost of them doing so is at least as large as the information you get out. So there's no free lunch here. Collecting more information doesn't help here. Okay, so to wrap up, and pull some strands together from that. Perhaps this is not so much conclusions as sort of final observations. One thing we get from this is that if I'm thinking of thermodynamics as a control theory, and if I'm thinking about thermodynamics as a theory, as a control theory of an antecedently specified theory, rather than just in its sort of abstract axiomatic form, then the irreversibility we get in thermodynamics is coming, at least in a part, from the time asymmetric constraints on the control operations. So if you look at the sort of thermodynamics characterized abstractly and axiomatically, then Harvey, Brown and Yosefin make a fairly persuasive case that in that framework, it's the assumption of equilibration in which we find the direction of time. if you're thinking about thermodynamics as the control theory of some antecedently specified mechanical theory, then I think we find it somewhere slightly differently. We find it in the fact that our control operations forward commute with some coarse graining, and that whole framework of describing coarse graining builds in a direction of time. But also, and this is the lesson I think that at least some bits of the foundations of statistical mechanics literature and philosophy of statistical mechanics literature don't recognize the full force of, even if we have a fully reversible and therefore fully time-symmetric thermodynamics, it still doesn't allow us to get past the Clausius state of the second law. So at least some of the temptation to say that the second law is an emergent or approximate or higher level framework is understating the sort of strength and rigidity of the relevant constraints. Okay, I'll stop there.
Okay, perfect. Okay, questions for David?
Explain exactly what aspect of control operations are time asymmetric.
Yes, I can, although I don't know how to say as much as I'd like to say here at the moment, and that's partly because I've taken a framework across from StatMech and I'm not completely sure it transfers. So formally speaking, what I'm requiring is, I've got the requirement of forward commutativity, which, as stated, you can see fairly easily how you time reverse that. But you've also got the requirement that the initial state of the system is one of the, and I should have spelled this out more explicitly, that the initial state of the system needs to be forward compatible in this kind of way. So if I start the system off in a state that's actually coarse-grained, and then I apply control operations that forward commute the coarse graining, then I get out the various results I'm discussing. If I start the system in a state that's not actually coarse-grained, but which is forward compatible in this way, again I get out the coarse-grained thermodynamics I'm discussing. But it's possible to have states here that have some very particular structure such that they're not forward compatible in this way, and in that case all bets are off as to how these things play out. And generically, if I start with a state that's forward compatible, in particular if I start with something like a uniform state and I apply a whole bunch of these control operations, the actual state I get out at the end is extremely fine-grainedly complicated and structurally messy. So if you then said, suppose you wrote down the time reverse of this framework, then you'd find that the state you got out at the end is not itself, I suppose you want to say, backward compatible with all of those processes. So it's kind of like, I mean, I think you see something very much like this in at least the way I think about non-equilibrium, StatMech dynamical laws, where instead of having choice of all of these U's, the U's are just the actual dynamics of the system. We're making the assumption that the initial state of the system is forward compatible that way. And that looks innocuous because it looks like that's just saying the initial state doesn't have a whole bunch of very delicate fine-grained structure that conspires to mess around with the coarse-graining assumptions and dynamics, but then the state we get out at the end of that is a state whose time reverse does have exactly that kind of apparently conspiratorial fine-grained correlation structure.
So just very...
Okay, well, just
sorry,
come back.
sorry, to pack some of that.
Yeah, sure.
First of all, when you went through the slide the first time, I assumed that there was a typo, but given what you said, maybe I'm mistaken. Your very last equation, did you meant to say row C, U1, and so forth, leftward? Like, should there be a C between the U1 and the row?
You mean here?
Yes.
No, intentionally not.
Intentionally not. Okay, so
if you look at it, if there was a C in front of it, then it would just follow from the equation above, yeah. And conversely, if rho equals C rho, then again it would follow from the equation above. So states satisfying rho equals C rho are automatically forward compatible.
Okay.
Just a really high level question about your goal. Is the goal to argue that one can think of thermodynamics as a resource theory, or that one should think of thermodynamics as a resource theory? Or control theory?
Yeah, at the super high level, I don't think I've said enough to make this completely persuasive, but at the super high level, I think one more or less has to. There are certain connotations of resource theory that I'm not quite sure I know what they mean, and I'm not sure I'd want to push into that framework, but do we need to think about thermodynamics as a theory of control operations rather than a theory of dynamics, then I think yes, definitely. The only caution there is that the term thermodynamics is used in kind of loose and variable senses. So, I mean, I was just at a meeting on the hour of time in Santa Fe day before yesterday, and I was thinking about my talk for this conference at the time, and I was struck that basically everyone was using thermodynamics and statistical mechanics as if they were synonymous. So I mean thermodynamics in an intentionally narrow sense. If you might, for instance, think that, say, the derivation of the actual equation of state of beta brass counts as thermodynamics, in which case that's not a control theory fact, that's just an objective fact about the equilibration structure of systems of that kind. And at some level, it's just terminology, but I think there's a certain virtue, at least in these discussions, of keeping the word thermodynamics for something that's much closer to the thing that one talks about as equilibrium thermodynamics in sort of textbook treatments. The weaker version of that is, if you like, there is a substantive chunk of the subject that needs to be thought about as under the framework of control theory, and that's the chunk that's concerned with things like the Clausius and Kelvin statements and the possibility or impossibility of a Maxwell demon and the ability to use heat engines and heat pumps. That thing needs to be thought of as a control theory. And again, it's sort of not clear to me what the alternative to that would be. I mean, it fairly manifestly doesn't have dynamics, and fairly manifestly the things that are written down and discussed are things about those sort of transformations.
Okay, there we are.
So, if we imagine that identity operations are also in allowed control operations and applying the last equation, then we get that 0 should be equal to rho for all states in the control theory if we want them to be forward compatible with all sets of control operations commuting with some C, right?
Sorry, say it again?
So is it the case that every state rho forward compatible with C and this U set of control operations necessarily have to be said that 0 is equal to rho? For example, if we take the set of control operations to be just identity.
So you're thinking put U1 through UN equal to identity and I'll get trouble. So I'm not saying that if I put U1 equals if I put all the U's equal to the identity here, this all just becomes C to the power 2n rho equals C rho.
Okay, so it's strictly weaker condition.
Because I mean, remember, C squared equals C is a starting presumption here.
Okay.
Yes.
Thank you. I probably missed this in your talk, so I was thinking about your summary slide. You say that the irreversibility comes down from the constraints on control operations.
Yeah.
And the time asymmetric constraints. I was wondering, how should we think about this constraint? Are they supposed to be understood in terms of mechanically, or are these kind of primitive notions in theory to be just taken as in addition to space and other things, there's constraints?
Yeah, good. Well, the compound answer is they should be taken in about the same way we take initial state considerations in non-equilibrium statistical mechanics. So, claim, if you want to understand, say, the derivation of the Fokker-Planck equation or modern versions of the Boltzmann equation or any number of time asymmetric macrodynamics in stat mech, the way you're doing it looks quite similar to this. You have a combination of some dynamics that plays nicely with the coarse graining and some additional restriction on the initial condition, which normally looks something like it hasn't got a certain sort of really nasty, delicate, fine graining structure that messes with the assumptions you want to make. And you can make that relatively mathematically rigorous, at least in some contexts. If you want to say, why is that reasonable? At some level, that's going to come back to how you want to think about the hour of time more broadly. So one story, for instance, is you want to say, it's heuristically reasonable to expect conditions of that kind to be the output of other processes of that kind, and it's reasonable to assume that the initial states of processes for that new process is itself the output of processes of that kind, and you track your way all the way back to some kind of cosmological boundary condition. So plausibly that's the case. On the other hand, we have, I think, at this stage of development of stat mech, we have much more ground to be confident that the way in which we actually apply this formalism involves those kind of locally set up initial state boundary conditions than we do to believe on that kind of unification of them. So while I'm pretty sympathetic to the unification story, I don't want to make it a necessary part of the account here. So for instance, if you've got some, at the other extreme, let's say, if you have what I've called in other contexts an inferential view of physics or of this bit of physics, and you think the right way to understand the initial state is as a consequence of what a reasonable agent could have set up, then you might want to say that the initial state can't have those kind of details because no reasonable agent could prepare it in that kind of way. I'm not ultimately super sympathetic to that way of thinking about statistical mechanics, but I think what I'm saying is largely neutral as to whether we should be sympathetic or not.
Is there easy way to see how they extend this to cosmological context or unification? We have constraints, I guess, would there be constraints on conditions or constraints on operations conducive to the global system?
Well, so distinguishing this framework, I mean, again, some of this is a bit clean. It's given how derivative and down the chain thermodynamics as a control operation is from cosmology, it's kind of easier to think about this in the stat-mech context, but in any case, this kind of property, this forward commutativity thing, that's a statement about the dynamics. So given a microdynamics, given a coarse-graining operation, you can say objectively whether or not there's forward commutation. To go from the dynamics to go from that dynamical claim to an actual closed form dynamical equation for the coarse-grained degrees of freedom, or in this case, a control theory for the coarse-grained degrees of freedom, requires this initial state consideration again. We don't have anything like enough control of the unity of science to tell a rigorous story to the effect that any particular consideration of what the boundary condition should look like is going to generate what the cosmological boundary condition looks like is going to generate any particular conditions of this kind in later higher level theories. I think there are pretty good hand-wavy heuristic reasons to think that if you don't bake in extremely delicate correlational structure into the initial state of the universe, or let's say the immediately post-inflation state of the universe, then it's unlikely to generate the kind of forward incompatible states later in the dynamical evolution. That strikes me as heuristically highly plausible, but let's not kid ourselves that we have sharp dynamical control of that question.
Rob.
So I'm still trying to get clear on the time asymmetry.
Sure.
Let me ask the following question. Once you grant that we're talking about a control theory,
Yeah.
so we have agents who are making interventions on the system,
Yeah.
there's already a kind of fundamental time asymmetry
Yeah.
there. And sort of,
Yeah.
An intervention is a time asymmetric notion. So it seems like asking about time reversibility is sort of a natural question to ask it in a dynamicist sort of picture, but in a control theory picture, it's unclear what you're asking. So are you asking, like, certainly I can't imagine agents that are traveling backwards in time and making interventions. So are you just asking a question, something like, if I imagine starting with the final state and doing a bunch of interventions which are required to be, for example, the inverse of somehow the operations that you did in the first sequence, then I recover the initial state. Is that?
I think something like that's probably the right way to go, because I agree with you that the mere fact you've set up this kind of framework makes it difficult to understand exactly what we mean by doing the control in the opposite order. It's kind of baked into the setup. But I think that's kind of right. I think, I'm not sure I'm fully consistent with this through the story. I think talking in terms of irreversibility rather than time asymmetry perhaps is a better way to do it in this kind of control context. And there I think it is something like you can make your way from A to B, but you can't make your way back from B to A. Now, this is what I was thinking, meaning when I was alluding to sort of Brown and Iffing's work on this. So, in their very sort of axiomatized, self-contained picture of thermodynamics, they want to say that nonetheless that's in an appropriate sense time reversible because you can just sort of effectively, the backwards processes are processes which cannot increase the entropy. I think the sort of setup here where we've actually got a sort of description of the micro state space gives a slightly more robust way to talk about when transformations can't be reversed. I'm not sure about that.
So do you have a theorem then which says, in response to my first question, you said, if rho is not forward compatible with C and U, then I can have a failure of time reversibility. So if I use the definition you just specified, that to be time reversible means a transition from A to B implies the transition from B to A. Can I use that, mathematize that, take that definition of forward compatibility and prove a theorem that says lack of forward compatibility implies failure of time reversibility?
I'm not sure. Lack of forward compatibility implies failure of time.
So this is what I thought you answered to my first question, but maybe I got that wrong. You seem to be making a connection between this forward compatibility and like you seem to offer it as an example of a failure of time reversibility. But maybe I misunderstood.
Yeah, so if I've got a forward compatible, I'm not 100% sure what the right way to say these things is, to be perfectly honest, but if I've got a forward compatible control theory, which is to say I've got a coarse-grained map, I've got control operations that forward commute with it, and I've got an initial state or family of possible initial states, all of which are forward compatible with it, that control theory is going to be irreversible in the sense that there's a whole bunch of transformations that I can't go backwards on those transformations even at the coarse-grained level. So in particular, the coarse-grained entropy is generically going to be increasing, it's never decreasing. So you can be from that.
Forward compatibility that implies the time.
Yeah, now there's a definition of time reversibility which I understand how to think about formally, but I don't know how to think about, I'm not sure I know how to interpret in the normal language of sort of dynamical time reversibility, which is something like, well, if I just formally consider these things backwards, if I consider some collection of final states and I just formally consider acting on those with the inverses of my control operations, and I look at the formal control theory I get from that, what relation does that bear to the original control theory? And I think in that sense, you can, if your condition on the final states just looks like the forward compatibility condition here, then you'll just get the same thing out backwards. If your condition on the final states is that they're the result of control operations of these kinds performed on forward compatible initial states, then the operation run backwards will look really different. It'll actually unravel all of the transformations. So there's something there that seems appropriately linked to the kind of way in which, in a dynamical context, if I have generic final states and run them backwards, I get the entropy increasing into the past, or systems becoming more spread across phase space into the past. If I take the actual states I get by taking generic initial states and running them forward, and then I run those actual states back, I just unravel the dynamics again. So there's at least a formal connection there. How much that can be used to be said interpretively, I'm not sure. It's less obvious than the state of reversibility, anyway.
More questions? Yes. All right, go ahead.
So have you thought much about, you seem to suggest that there was a kind of spectrum of possibilities for these coarse grading operations. You gave two examples.
Yeah.
But that there could be an arbitrary number of other examples. So I was thinking about how to formalize that in the resource theory framework. And so quantumly, for example, the basic resource theory of thermodynamics starts off by saying, suppose you can do all energy preserving unitaries.
Yeah.
So that's akin to what you assumed, where you just have access to any symplectic morphism in the phase.
Yeah.
And in the resource theory framework, once you give me that you allow all energy preserving unitaries, the set of states you allow for free, it becomes very constrained, right? So I can only allow the family of thermal states for some fixed temperature for free without making the whole thing trivial. So start telling me what unitaries you're allowed actually basically fixes up to one parameter what the resource theory is. So if you said, okay, now we're not going to allow all energy preserving unitaries, but we're going to maybe allow only those unitaries that are generated by certain operators. Like I can do translations, I can do say momentum shifts, and maybe a bunch of other stuff. But it's coarse-grained, right? And then you would get a new resource theory. But you can start to sort of classify what are the resource theories I can have, right? Tell me exactly what generators I'm allowed, and that specifies exactly. I just close under the group action. I get some group of unitaries, which describes exactly what I'm allowed, and there's going to be sort of a finite number of possible. You can control nothing, you can control everything, and there's every subgroup of unitaries in between, and that's it. Those are all the control theories, and it's not arbitrary. I presume that there would be something similar in the classical case. I can generate a group of symplectomorphisms by talking about, you know, which generators I'm allowing closing of a group action.
Yeah, I would think so. I mean, particularly since pretty much everything I've said here has a pretty straightforward translation into quantum language. I was really just using classical language for ease of visualization. I guess there's a difference of philosophy in that the sort of situation I was more considering was sort of what's descriptive of the thermodynamics we have, and how do we understand how that thermodynamics is constrained relative to the sort of reversible thermodynamics where I have extremely wide resources available. And I think, so the thought there is that the sort of coarse-graining maps here are going to read off the actual dynamical restrictions of what we can do in those situations. And it's a bit like the way in which the coarse-graining maps that come up in non-equilibrium statistical mechanics are just read off the actual facts about dynamics there. So I think there ought to be a translation there, but I haven't thought about it in those terms. And it'd be interesting to do so.
Any more? Well, we're running a few minutes late, but it's all quite manageable. I suggest we need, do you want to say 10:35, 10:40?
Yeah, let's say 10:35. That gives us time to
10:35
set up the site, get contact
and
with
we're
you.
in business, and so it remains only to thank David very much.